Today will be our last day of new material, which is good because it's the last day of class, right? We just have a little bit more to cover inside of spherical geometry. Some differences to point out between spherical geometry, elliptic geometry, and then, I didn't say that right, spherical geometry, hyperbolic geometry, and Euclidean geometry. And then we'll talk about your final that's happening next week. So where we left off last time was talking about how to measure angles. And using that idea, basically what we did is we took tangent lines where those angles were, and we measured the angle between the tangent rays, if you will, and that angle would be the same angle that we would be referencing inside of the sphere. And so just as a sort of visual imagery example of what's going on, go ahead and take a sphere and let's draw in a specific triangle. So let me get this cooperating for me. Here's my sphere. And the triangle that I want to draw in is one that cuts right here at the front. That was terrible. That's a little bit better. Actually, let me change the color of this. So here at the front, here on the side, and here, okay? So there's my triangle that I'm trying to identify with you. And just as a reference point, let me actually give you some vertices for those coordinates so that we can talk about them very concretely. So we'll call this one C, this one is A, and this one's B. And our point A would be the point 1, 0, 0. Our point B would be the point 0, 1, 0. And our point C would be the point 0, 0, 1. So in three-dimensional geometry, like if you're thinking Euclidean space, this would be, three space. You would have it from the origin, one up, one left, one right. That's what you're looking at, sort of in the terms of a corner of a room or something like that. Now remember, we're talking about arc lengths and measurements earlier. So if we were to measure the arc of AB, and remember the way that we measure that is, or notationally, we talk about the measure of this arc AB is measured AB. And if we're measuring around this, how far am I going in terms of an angle measurement? What would the angle be? It'd be 90 degrees. And in radians, that would be pi over 2, right? So we're going pi over 2 radians, and because our radius is 1, that ends up actually giving us just pi over 2. So the length of this would be pi over 2. Okay, it's r theta, and theta is pi over 2, r is 1. Now, if I follow that same logic, what would I get for my arc length for BC? Same thing. And for AC? Same thing, right? Whoops. This is what happens when you're talking, when you're writing. Pi over 2. Pi over 2. So what would the angle sum then be for all of these? What happens when we add them together? Yeah, we get 3 pi over 2. So if I were to add this angle and this angle and this angle, which are all pi over 2s, I would get 3 pi over 2. What would that be in degrees? Just because we think in degrees sometimes better. What's 3 pi over 2? It's 270. What was this shape? A triangle. Does that feel a little weird? That's different, because you're used to triangles being 180 in Euclidean. What were they in hyperbolic? Do you remember? They were less than 180. So at best right now, all we can say is that these are greater than 180, okay? They're not all 3 pi over 2. This one just was. It's a nice visual example that we can all sort of, or at least mostly picture, because it has a nice three-space Euclidean component we can talk about. But it's more than 180 degrees for triangles. So that's the fact number one we're going to write down is the angle sum of any triangle in spherical geometry is greater than 180 degrees. Okay? So when we talked about the hyperbolic case where it was less than 180, and that was sort of the best we could say is that it's less than 180. I don't know how much it is, but it's something less than 180. We talked about how far off it could be from 180, and we had a name for that. Do you remember what we called that? It was the defect, right? The defect was how far away are we actually from 180? Well, in this case, we still, again, are away from 180, and how far away? Well, this is actually defined as the excess. So the excess, right, in excess of, right, in the excess of a triangle is this measure, we'll call it epsilon of triangle ABC, which is the measure of angle A plus the measure of angle B plus the measure of angle C. It's the three angles added up minus 180. When we did defect, it looked exactly opposite this. It was 180 minus the three angles. A cool fact in spherical geometry is that angle is a valid congruence criterion. We've seen it happen before. That was also true in hyperbolic geometry. So it fails in Euclidean geometry, of course, right? We can have similar triangles, but in hyperbolic geometry, we talked about the fact that similar triangles are actually congruent. Well, they are here too. Similar triangles are actually congruent. One more additional fact, very similar, and it will come as no surprise given the one we just did, is that the angle sum of any quadrilateral in spherical geometry, what do you suppose we can say about it? You got it. It's greater than 360. Okay. Imagine taking two triangles that we know are both greater than 180 and connecting them together, as long as you've got to have, one of the sides have to be congruent, of course, but connecting them together, we're obviously going to be greater than 360. So that makes sense as well. Not only that, but that means we do not have what in spherical geometry? Squares, rectangles, right? Because squares and rectangles have how many degrees? 360. So there's no squares, rectangles. We can just say rectangles in spherical geometry, just like there wasn't in hyperbolic geometry. All right, a few more cool facts before we leave spherical geometry. We're going to look at a few more things. A definition. A double lune is a region on a sphere bounded by two great circles. So if we draw a great circle here, and we draw a great circle over here, then this is what it's describing. All right, two great circles. And we're about to reference this in a moment. The angle here, we're going to call it alpha, this angle that's being created by this intersection. So a few notes about alpha. First, alpha is between 0 and pi. And if the great circles are actually distinct, they're different, then you could use strictly greater and strictly less than on this particular one. You don't need the equals parts, okay? Fact number 2. If you did have alpha equal to 0, then hang on, I should have shaded this in. Let me come back up and shade. One more thing on our drawing. I didn't actually shade in yet, and I'm about to reference it, so that's unhelpful. This area is what's being referenced when it said region. Okay. There are days that technology is just so frustrating, and then there are beautiful things that you can do that I would have trouble doing on the board, and this is one of them. So drawing spheres and things like that. Okay, so for alpha equal to 0, if it actually equal to 0, then the area, that red area would be what? Yeah, it'd be 0. Area would be 0 if the two great circles essentially were the same thing. And if alpha equals pi, this is sort of the antithesis of this, the exact opposite. We would actually say that the area of the double lune is the whole sphere. The surface area of the whole sphere. What would the surface area of this sphere be? How do you find the surface area? Do you guys remember surface area formula for a sphere? Yes, ma'am?
Is the shaded area, does it not go to the back as well?
It does. I'm just afraid that if I start shading, that I'm going to end up confusing my graph.
Okay.
But yes, it does. The shading area definitely goes on the back. Maybe I can try. I'll try. I will try. It would shade in back here as well. That's not too bad. I think it's okay. Yeah, so it would go all the way around. It looks kind of like, I don't know, like a bandana or something, right? It's got these two, but it's a bow tie is what it is. It's a bow tie at the front and the back. That's what we actually have is a bow tie. Look, anyway. All right, Matt, no pressure, but we need for you to tell us what is the surface area of a sphere. Nobody else knows, so if you do, I should give you something for that, right? No clue. The surface area for a sphere, I'm going to give you a formula just so you know it. It's actually 4 pi r squared. This, if you remember, geez, anybody remember the volume for a sphere? 4/3 pi r cubed. What happens if you took the derivative of 4/3 pi r cubed? Did anybody remember that from calculus? I know I talk about it when I teach calculus. I can't remember which calc it shows up in, but yeah, that's the relationship between volume and surface area actually for all of your solids. Cool, right? Yeah, so, oh, it should say thing. Yes, thank you, Hannah. It's cubed, 4/3 pi r cubed, and then you take the derivative and you get 4 pi r squared. Okay, so if, and it's true, it's not just an if, but because the surface area formula is 4 pi r squared, And what is our radius? In spherical geometry, what's the radius we're working with all the time? It's 1. So what is the surface area of this entire sphere in spherical geometry? 4 pi. So if we have a alpha value between our two great circles that's actually the whole thing or approaching the whole thing, you can kind of think of a limiting process. The area is approaching 4 pi, the whole sphere. Okay. Fact. The area of the double lune with angle alpha is alpha over pi times 4 pi, which ends up being 4 times alpha. So where's this formula coming from? Well, you know that 4 pi is the area of the whole sphere, right? The alpha over pi is actually measuring a proportion. If alpha is your measurement and pi is out of a whole, then if we take alpha divided by pi, we're getting the proportion, the ratio of what you're actually having for your angle measurement. So that's where that's coming from. Nicely enough, of course, if we multiply these, we see 4 alpha because the pi's cancel out, which is very friendly. Okay. So what we're going to do now is we're going to consider a spherical triangle with angles alpha, beta, and gamma. And we're going to try and draw it. So here's my alpha, here's beta, and here's gamma. Okay, I didn't draw in the dotted lines at the back, but you can all pretend like they're there, right? I know you can. We've got good imaginations. Okay, notice the... Actually, I think I'm going to have to draw it. Maybe. We'll see. The antipodal triangle on the back side of the sphere which is congruent to the original. So as I was preparing for this lesson in my mind, I thought what I'd really like to do, and then obviously I didn't do it because I forgot, is I really wanted to do what Hannah was suggesting last time, which was about rubber bands. If I were to take a ball and I were to put these 3 rubber bands in such a way that I created this triangle, you would see the triangle on the front and you would see a congruent triangle on the back, mirroring the same one we had before, okay? I can't draw that very well. Even if I draw my dotted lines in, I don't think you're going to see them very well. I'll try, and we'll just see what happens. it's not too bad. Can you see it? It's flipped upside down, right? So what was the top of my triangle is now the bottom of my triangle on the back. I can see it on my version pretty well, but I've got mine zoomed in pretty good. The triangle that I'm seeing, let me see if I can mark it anyway, is right here. Is that okay? That's the antipodal triangle it's referencing. Obviously in the lower hemisphere because originally it was in the upper hemisphere and so forth. So what I'd like for you to do is to consider each of those great circles, those arcs, those lines, if you will, that are creating the sides of the triangle. And they actually create double lunes. So consider the double lune with each of these pairs of angles, which each of these pairs of great arcs or great circles, which create the angles, with angle alpha, beta, and gamma. So as I'm creating this, I have it's not drawn very well. Here's alpha up here at the top. I get my beta on the right. Here's beta. Oops. And over here is gamma. Okay, so there's three double lunes. If we shade all three lunes at once, all parts of the sphere are shaded at least once. With the original antipodal triangles, I said that a little bit funny, the original and antipodal triangles, being shaded how many times? Right. Being shaded 3 times. So check this out. The area of the alpha double lune plus the area of the beta double lune plus the area of the gamma double lune is going to equal the area of the entire sphere. That's what we've just said. Plus twice the area of the original triangle. Plus twice the area of the antipodal triangle. So let's see if we can identify what some of these values are. What's the area of the alpha double lune? We talked before about how we find area over here, right? I think when we're back. How do you find the area of a double lune? It's 4 alpha. So this is 4 alpha. What is the area of the beta double lune? 4 beta, and the gamma double lune. 4 gamma, right? What's the area of the entire sphere? 4 pi, we did that one before. And then our original area of our triangle, we don't have that value because we made the triangle arbitrary, so we're just going to call it A for now. And so if A is the area of the original triangle, what's the area of the antipodal triangle? Also A, yeah. So this is 2A. So these are our values that we've set up now. So I have 4 alpha plus beta plus gamma, if I add those together and pull the 4 out, equals 4 pi plus alpha, because this 2A, or not alpha A, A is what I meant. 2A and 2A is 4A, so I can pull the 4 out of those. So what we've actually got here is that alpha plus beta plus gamma is equal to pi plus area of the triangle. And we can actually set up the equation of the area of the triangle is actually alpha plus beta plus gamma minus pi. And the conclusion for that then means, what we have found, so to speak, is that the excess of a spherical triangle is equal to its area. Because this is exactly what we called the excess a moment ago. That was the formula we had, right? Pi minus my 3 angle measures. All right, so the last thing I want to talk about inside of spherical geometry is what we ended with in hyperbolic geometry and elliptic geometry. Euclidean geometry is what I meant to say before. We were talking about transformations. Remember that? What kind of transformations do you remember that we talked about over the last couple of weeks? Tell me something. Reflections, that was one. Rotations was another one. Translations. What was it? A glide. I think those are the 4 we talked about, right? And we talked about how they can be composed of reflections. We can create a rotation by doing 2 reflections and these kinds of things. Well, we're going to look at what happens when we talk about motions and isometries on a sphere. Okay, so motions or isometries of the sphere. And all the ones you guys just mentioned were motions or isometries. There are other transformations, like dilations, for example. They don't preserve length, so those were not isometries. We're looking just for the isometries. So what I'd like for you to recall is that a motion of the sphere, or a motion would be, in this case, of the sphere, is a transformation of the sphere that preserves length. Lemma 1 says the following. Let T be a transformation from the sphere to itself. So let it be a motion, specifically. A motion of the sphere. Then for all points P and Q in the sphere, the measure of angle PO, remember O is the origin, Q, would be the measure of angle T of P, it's the P after the translation, O, T of Q. A lot of times we call them P prime and Q prime when we do the transformation like that, but they're being defined like this time, which is fine. Note, a reflection of the sphere is a reflection across a great circle. We'll call it M for now, because then we can actually talk about the fixed points. What points would be fixed if we reflected across the line M? Yep, the points on M, just like in Euclidean and hyperbolic geometry. Points on M. Let's talk about rotations. Note, a rotation of the sphere is a rotation about the diameter the fixed points are the two antipodal points on the diameter. And we have a new type of transformation in spherical geometry. This is called a rotoreflection. And if you had to guess by the name, what would you think it means? You're going to have to talk loud, though, because that fan just kicked on. What would a rotoreflection maybe be? It rotates it, but that's what a rotation did. And reflects it. You got it. Rotation and a reflection. All right, so this is the composition of a reflection across a great circle so we'll call that great circle M, which is the intersection of gamma in our sphere and a rotation about the diameter it's a specific diameter though, it's a diameter perpendicular to gamma. Proposition: every isometry of the sphere is one of the following. It is either a reflection, a rotation, or a rotoreflection. One of the very last things that we left in our last section with geometric transformations was talking about things being orientation preserving or reversing. So in regard to that idea, reflections and rotoreflections are orientation reversing. Now that fits in with what we did before. Reflections were already orientation reversing when we did it before. And we talked about the fact that if we did an odd number of reflections, that would always be orientation reversing. And both of these have an odd number of reflections. And a reflection is 1, a rotoreflection has 1, so this makes sense that we would end up with an odd number of reflections and it would be orientation reversing. But rotations, how did we get rotations when we talked about them before? A rotation was a composition of what? 2 reflections. So when we had an even number of reflections, it was rotation, or it was orientation preserving. Okay, it's the same thing here. The rotations are orientation preserving. Couple more details, and then we're going to do a comparison chart. I wanted to have this printed out for you, but I didn't have time to get that to happen for it, so we're going to write it out together. A couple definitions first. The map from the sphere to itself, F on the sphere to itself, defined by F of P equals negative P, is called the antipodal map. note, you can think of the antipodal map as a reflection across the line M, which is the intersection of gamma and S2, severe, followed by a rotation about the diameter perpendicular to gamma by an angle pi. Hence, the antipodal map is a rotoreflection. So that's an example of a rotoreflection, the antipodal map. All right, let's do a, it's not a thorough comparison, but a comparison nonetheless of our three geometries. So we have three different types of geometry, and they have some very different characteristics, each of them. What was the first type of geometry you came into this semester knowing and I would say loving, but maybe you didn't love it, I don't know. But you knew it anyway. You were familiar and aware of it. What was it? Euclidean. So we will do a column for Euclidean geometry. What are you saying over there, Seth?
I just love math.
I know, don't we all? Euclidean geometry. And then we learned next about which geometry. We spent quite a while in the next geometry. Hyperbolic, right? Hyperbolic. Sometimes also just called non-Euclidean, so hyperbolic geometry. And now we've spent basically a day and a half, and we've hit on it before. We've mentioned this one before. Our last geometry was spherical geometry. And we talked about, as a reminder, that spherical geometry is not a model for neutral geometry, which was something different. So the first thing I'd like for us to think about is how parallel lines differ in Euclidean geometry. So what can you tell me about parallel lines that you know is specific to Euclidean geometry? You don't have to say it with all the right math lingo, I'll write it down. But what do you basically know? They have what? They have no point in common. Okay, that's true for all of them, though, because that's a definition of parallel. So can you go a little further with Euclidean? We think about it like that. It's not defined that way, but we do think about it much like that, whereas when we drew like asymptotically parallel things in hyperbolic geometry, that certainly didn't happen, right? Okay.
One parallel line through a single point to the...
Yeah, that's actually a really good sort of picture. So if you have a line and you have some other point somewhere else, then in Euclidean geometry, there's exactly one line that's parallel here. What happens in hyperbolic geometry? There's infinitely many points or lines parallel through that point. And what happens in spherical geometry? There are no parallel lines. So that's the difference in our parallel postulates and those different geometries. So let's write them out sort of officially. So given a line L and a point P not on L, it's supposed to be a capital P, P not on L, there exists a unique line M such that M is parallel to L. I hope you're getting more comfortable with the notation as we continue to use it. And that's not what happened in hyperbolic geometry. So here we were given line L, point P not on L. And what existed? Yep. There exist infinitely many lines through P parallel to L. And while we could write out a more detailed description, I think the way that Hannah said it was really concise and very nice. In spherical geometry, parallel lines don't exist. And again, remember, lines are great circles, and great circles always intersect one another. In how many points? 2. Okay, so that's our first major difference between our 3 geometries. And because of that, it creates some interesting things. So let's talk about triangles. Tell me what you know about triangles in geometry that you're used to from high school, Euclidean geometry. The angle sum is 180 degrees. You got it. So the angle sum of a triangle equals 180 degrees. What happens in hyperbolic geometry? It's less than. The angle sum of a triangle is less than 180 degrees. And in spherical geometry, yep, the angle sum of a triangle is greater than 180 degrees. Awesome. So we haven't talked about this too much in the sense that we've not used these words, but we can actually talk about Euclidean geometry being sort of like geometry in a flat space, right? We think about it that way. That's called zero curvature, this idea of being flat. When we look at spherical geometry, I'll jump over there, we actually talk about that having positive curvature. And you can imagine how that sort of plays out. You've got this positive feature going on, so positive curvature. And so what do you think is going to happen if I need to write something in hyperbolic? It's negative curvature. Okay. Yes?
So if the curvature in hyperbolic is negative,
Mm-hmm.
would the inside of a sphere, like geometry on the inside of a sphere instead of the outside, be a hyperbolic geometry?
You can think about it that way. If you think about the way that we sort of imagine, reflecting from the sphere down into a plane to draw our hyperbolic space, that has a very much the effect that you're describing. Yeah. Yeah, definitely. All right, a couple more things. Let's talk about quadrilaterals and then motions. What can you tell me about quadrilaterals in Euclidean geometry? What's the angle sum of a quadrilateral? Yes, it equals 360 degrees. So what happens when you do the angle sum, of a quadrilateral in hyperbolic geometry? Yes, it is less than. I'm going to fix my sign. It's less than 360 degrees. And what about in spherical geometry? It's greater than 360 degrees, right? And then the last thing I want to talk about is our different kinds of motions. Since we just did them, let's start with spherical geometry. What motions did we just discuss inside of spherical geometry? You got it. So we had reflections. We have rotations. And we had rotoreflections. Let's go back to Euclidean geometry and see if we remember those. What motions do we have in Euclidean geometry? You told them to me earlier. You didn't realize that you were telling me, but what transformations do we have in Euclidean geometry? Reflections. Reflections and rotations are both there. Let me write those down. You mentioned one, Kennedy. Glide. And there's one more, and I think it came from this side of the room when we were talking about it. Translations, that's the last one, yeah. Translations. And inside of hyperbolic geometry, we also have the same ones that I just mentioned in Euclidean geometry, plus there's one more. So we have reflections, rotations, glides, and translations. And does anyone happen to remember the one additional one that we had inside of hyperbolic geometry? We didn't spend a lot of time talking about it, but we did talk about it. It's called parallel displacement. That was our last one. So I wanted to go over this kind of chart because this is a pretty good review for the things that we've looked at this semester and the differences that we've found, some of them, between our different geometries. Any questions before we take a look at final exam stuff? All right.